Hi, welcome. In this video, we will talk about suffix trees, their background, how to construct one, and some applications. So let's get started. Suffix trees are used to effectively search for strings and substrings. A suffix tree is a tree in which leaf nodes that indicate the ending of a suffix in an original string also hold a position at which that suffix started. Additionally, paths of nodes that only have one child are combined into a single node to preserve space. Also, there's an added character at the end of the string, which we will get to. This just now was a mouthful, so we need to cover some background, and let's start from what prefix and suffix means in this context. Let's look at an example of a string that can be partitioned into alpha, x, and omega parts. Each of these parts, alpha, x, and omega, are 0 or more characters combined into a single string. A prefix of a string is some characters that come before more characters. A suffix of a string is some characters that come after other characters. So in this example, x is a suffix of alpha x, and x is also a prefix of x omega. Tries, sometimes also called prefix tries, are search trees. The connections edges show how characters come one after another character, and at each node's data, if the data is bigger than 0, we know that a word ends here. We can use tries following from the root to bottom to find out if, for example, a string belongs to a language, and if we fall off a try, we know that our string is not in the language. A suffix try is a try where the language from which it is built consists of all suffixes of a single string. Consider a string nonsense. To get all possible suffixes, just write out all strings in that string, starting from 0, then from 1, and so on. Then, insert all those suffixes into a try, and now we have built a suffix try. Same operations from before apply to this try, but what the try contains now have changed. So instead of language of words, it now contains all suffixes of a single string. Now add a character to the end of this string. Such a character must not have been previously seen in the string, and additionally, when ran through the sorting algorithm, it must come up on top. So it must come before every other character in our language, hence in the string. Again, build all suffixes of this new string with the $sign in our case appended. You can see them sorted in this picture on the bottom left, and insert those into our try. The next step is combining consecutive nodes that only have a single child into one big node, so to say. The children with only one child are useless, because they indicate that at least one more character comes after this character in the substring suffix without forming an actual suffix yet. Those nodes are kind of useless, we call them silly nodes, so when combined, we use less space and end up with what we call a Patricia try. Lastly, a suffix try is basically a Patricia try with some additional information. At the leaf nodes that indicate that a suffix ends here, we want to store the index pointing to where the substring started, or the suffix started. So in our nonsense example, the rightmost leaf in the tree sense started at the index 3. So this is what a suffix tree is, and this is what we want to build. Again, given all the background, let's summarize what a suffix tree can do for us. The leaves indicate the starting points of the respective suffixes. Nodes with a single child combined to preserve space. If m is the length of the string t, the number of nodes in the suffix tree is bound by the big theta of m. So how do we build the suffix tree? For the purpose of this presentation, we will assume we have already efficiently computed a suffix array, which contains all suffixes of the string, sorted, and the LCP, longest common prefix array. which is shown in the orange column in the picture. The LCP, longest common prefix array, says that, for example, between substrings starting at 8 and 7, there is overlap of 0 characters. Hence, length of the shortest common prefix is 0, but between indexes 5 and 2, for example, that correspond to suffixes NSE $, and NSE $, there is an overlap of 3 characters. Hence, the LCP is 3 there. Notice that zeros happen when we jump from one subtree to another, indicating that there are no common prefixes, because we basically follow a completely new path from the root. So, the root has 4 children, hence there are 4 zeros. Here, consider the array that has a sorted suffix array as shown on the right, and an LCP array again indicates where there are overlaps in the substrings. We want to build a Cartesian tree that fuses together the nodes with the same values, if one becomes the parent of the other. This is what we end up with from our array, but now we're still lacking some information, like where do the children actually point to? So now we need to run a depth-first search over the tree and connect the missing children to the tree in the same order that they appear in the sorted suffix array. Assign labels based on the values in the LCP, and we have built a suffix tree. It took us big O of m time, again, given that we already have the suffix array and the LCP array built, which of themselves have really clever algorithms to build efficiently. So here's a summary of our algorithm. Now, where can this be used? We can use the suffix trees to efficiently search over really long strings of the DNA, to find overlaps of the, for example, healthy and unhealthy parts, also to find mutations. Outside of biology, an obvious example is string matching for large entries that have to do operations on strings, like when you search something on Google or when DNS maps to an IP, which can also be done obviously with a really fast database, but still. Additionally, suffix trees can be used for string compression and therefore data compression. This concludes our short presentation of the suffix trees, which can be built in OM time, given that we know what's going on and also already built suffix arrays and LCP arrays.